Organic light-emitting diodes, or OLEDs, require a combination of electron injecting layer and a hole injecting layer. The combination of electron and hole is where the emission comes from. Each layer has to be suited for transferring either electrons or holes. In this example, we have two cut molecules, and we want to analyze whether they would be good HTL or ETL layers. We can analyze this by plotting the geometry coordinates of the optimized molecules and recording the energy given to us by the Orca software, as well as downloading the output log to check the HOMO and LUMO energies. In order to work out which state is more stable, the singlet or the triplet, we have to plot the XYZ files given in this NanoHub tool Orca. It needs to be on geometry optimization, and advanced settings need to be on. The only step that fully needs explaining is this one. You need to upload the .xyz file of your selected molecule. After that, you need to remove the number at the very beginning, else you will get an error. Once all these settings are correct, you can then go on to plot the molecule and get the total converged energy of the molecule. It's worth jotting this down, as well as downloading the output log for later use. Here you can see the energies of the singlets, triplets, cations and anions of all of the molecules from the PA molecule and the PB molecule. In this we can see that the singlet has mildly lower energy than the triplet, meaning it is more stable. As well as this, we can work out the electron affinity and the ionization energy from these molecules by working out the difference in energies between the singlet and the cation. The electron affinities and ionization energies are given here. It is also worth noting that when doing cations and anions, you have to change the spin to 2 and the charge to its respective charge. And when you're doing triplets, you need to change the spin to 3. Using the output logs from Orca, you can find out what the energies of the HOMO and LUMO are. If we look here, you can see the number of the orbital, and if it's occupied, and then the energy in electron volts. Scroll down to where one is not occupied. You can see that this is the highest occupied molecular orbital, and this is the lowest unoccupied electrical orbital. We can do this also for our PA molecule. Using these HOMO and LUMO values, we can in fact work out whether these molecules are ETL or HTL type OLEDs. First of all, we can see from the diagram that the lowest HOMO value belongs to the ETL, and that the highest LUMO value belongs to the HTL. If we apply this same logic to our PA, our neutral or emission layer, and our PB molecules, we can see that our PA has the highest LUMO, and that our PB has the lowest HOMO. So using this, we know that our PB is our ETL, and that our PA is our HTL. As well as this, we were asked to plot the HOMO and LUMO for both molecules. Here I have the HOMO for the PA molecule, and here I have the LUMO for the PA molecule. Here I have the HOMO for the PB molecule, and here I have the LUMO for the PB molecule. The final problem we had was to simulate the unfurling of alpha helical protein structures we were given the molecular dynamic files. We were told to plot them in a NanoHub resource called stretchmol, and then download the VMD files to plot on VMD. What we need to do is plot the stretching of the alpha helical protein that we need in this tool on Orca. I've just done the first one, so I'm going to take you through how to set it up. Go over to initial geometry, and you have your uploaded data. You need to upload your initial PDB file, your structural file, and your fixed atoms file. If you look here, we have fixed.pdb, we have the PSF file, and we have the PDB file. Then move on to Smd Parameters. You have the uploaded, where you upload your SMD PDB file, and then you put the velocity to 0.05 because we don't want to be sat here for hundreds of hours. Put the direction X for this simulation at least. And then for the final simulation parameters, you upload the parameters file. Put the temperature at 300, and for this one we want 10,000 steps. We then run the simulation and wait. It's simulating 10,000 steps of a stretching simulation, so it will take quite some time. At the end of the simulation, you should have this energy plot. What we're going to do is go up to here and go into the VMD movie files, download the zip of this, and then you can use that to plot in VMD the simulation. Now the overall aim is to have this play the entire protein stretching simulation. This is the one for the 5,000 step calculation. I've slowed it down slightly because at first it was far too fast for anyone to actually understand what was going on. You can see clearly the protein unfurling and the water molecules around it reacting to said unfurling. In a similar fashion to the 5,000 step one, I am going to do the 10,000 step x-axis. First of all, you load in the molecule, and then you click on the molecule and load data into molecule. This is the trajectory of the molecule. First, the PSF file is the molecule itself, and then the DCD is the trajectory of it. You load it in, and you can see this is what the molecule did during our simulation. You'll notice it looks slightly different to the previous example. To fix this, we go on to representations, create new rep, put it to new cartoon, and color it by secondary structure. Click apply, and then we can play again at a slightly slower speed. You can again see the unfurling of the protein along the x-axis. Here we have the 10,000 step on the z-axis instead of the x-axis, and as you can see, instead of stretching out along the x-axis, it's stretching along the blue z-axis, so towards us in this instance, whereas the previous examples were along this axis here. The final file we did was the 100,000 step, which as you can see is noticeably larger, has a number more frames than previous examples. The proton unfurls and just shoots off into the distance. The water molecules buzz around it and then remain where they are. I must go, my people need me.